Today's lesson is 8.6 on probability. First, we'll have some definitions here. An experiment is a probability whose result is uncertain. Outcomes are the different possible results of an experiment, and sample space is a set of all possible outcomes of an experiment. Event is a part of the sample space. So the probability of an event has n of e equally likely outcomes, and its sample space S has n of S equally likely outcomes. And the probability of the event is, probability of event happen as always, basically number of ways event can happen over number of total ways. That's what the n is talking about here. So it has basically, this is event E has X ways it can happen. Out of the total number of ways is say Y, so the probability is X over Y. Right? This is what they're saying. Next, determine the sample space for a given experiment. A six-sided die is tossed and a coin is tossed twice. Right? So we have a dice that can give us values 1 through 6, and a coin that can give us heads or tails. So our first option would be, let's say, 1, heads and heads. Second option would be 1, heads, tails. Third option, we'll continue the pattern. Now we're going to go 1, tails, heads. And then last option will be 1, tails, tails. Now those are the 4 options just for 1. Right? Now there's 5 other numbers, right? We could do 2, head, head, 2, head, tail, 2 tails, head, 2 tails, tails, and so on. So here are the other potential options. I'm not going to say them out loud, but clearly 6 options for the first, 2 for the second, 2 for the third. 6 times 2 times 2 gives us 24 options. So there's quite a bit of work there, so some of them were pre-typed out for you. If you have any questions on how that works, again, feel free to ask through email or message. Next one is 2 marbles are chosen without replacement. So meaning we take one, then I pick another without putting it back in, from a bag containing 3 red, 4 blue, 2 green, and 1 yellow. Right? What are our different options? Right? So we've got red then a red then a blue, red then a green, red then a yellow. Those are all my red options. Next, red first options. Next, I've got blue then a, keep going. Green then a green, green then a blue, green then a red, green then a yellow. Then how about yellow blue, yellow red, yellow green, and we're missing our blue set. We're missing, right, what about blue and blue, blue and red, blue and green, blue and yellow. And those are our sets. Let me get the parentheses. So those are the different sets we have down there. Okay, so that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It is a weird number because yellow only has 1. Right, so that kind of changes why there's a different number of outcomes than the last one where we can just kind of multiply. Find the probability of getting exactly 2 heads if we toss the coin 4 times. So I drew out the sample space, and it took quite a while just because of size, but first coin can be heads or tails. From there, the second coin could also be heads or tails, and then we keep containing this tree, keeps growing. Third coin can be heads, tails, for all the 4 different options we already had, and the same thing at the end, heads, tails, head, tail, head, tail. So if you count the ends here, this end stands for head, 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 head. This end stands for heads, 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 and tails, and so on. So looking for the ones that are exactly 3, so I'm going to mark the ones. So we've got heads, 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 that's 4. So heads, head, head, tails, there's 1. Head, head, tails, head, that was 3 as well. Head, head, tails, tails, no, it's only 2. Heads, tails, head, head, that was 3. Heads, tails, head, tails, nope. Heads, tails, tails, head, head, tails, 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 heads, heads, head, there's the other one. And the rest of them are only going to have 2 or less. So tails, head, head, tails, tails, head, tails, head, tails, head, tail, tail, and so on. Right, going through the trees. And so we have 1, 2, 3, 4 options out of the 16 for probability of getting heads. So the probability is 4 over 16, which simplifies to equal 1/4. The probability of getting at least 3 heads. Now this means 3 or more. So we're going to look at the 4 out of 16, and we're only adding 1 more. The one we're adding is this one right here, because that is 1, 2, 3, 4 heads, is more than 3, but this said exactly. So we didn't count it last time. So now I have 1, 2, 3, 4, 5 total options, 6 out of 16, and so our probability is 5 over 16. Next, find the probability of the experiment of selecting one card from a deck of 52 cards. I explained kind of how cards work from the last one. If you're not familiar with your typical ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king deck of cards to play like solitaire or etc. with, but that's what they're talking about. So a card from 2 to 7 inclusive, meaning including 2 and 7. So counting them out, 2, 3, 4, 5, 6, 7, those are 6 options, and there are 4 of each of those. So we have 6 over 13, funny looking 6 there, 6 over 13 for total number of options. Now, you could have also done 6 times 4 over 52, but this is 6 of the 13 card types, so 6 over 13 is our answer. Next, the card is a heart, right? There's hearts, diamonds, clubs, and spades. So there's 1 of the 4 different suits, so 1 over 4. Now, technically, there's 13 heart cards out of the 52 total. That would also have worked, however, we want it simplified. Lastly, the card is a jack. That was 1 of the 13 types, so 113. Mutually exclusive. That would be where 2 events do not have an outcome in common. However, what if they do have one in common? Right? So, what's the point of that? Well, we're talking about the union of 2 events. If A and B are events in the same sample space, then probability of A or B occurring is given by probability of A union B equals probability of A plus probability of B minus the probability that they have an overlap, right? So if there's a you'll see an example in a second, so I don't want to spoil it. But for example, with cards, you could have, probability of a face card and probability of a heart. Well, some face cards are hearts, so we would need to subtract the pieces that appear twice. Otherwise, they would be counted twice. If they're mutually exclusive, we don't need to worry about this, because then that means they don't have any outcomes in common, but common. So probability of A or B, if they're mutually exclusive, is probability of A plus probability of B. Mouthful. Find the probability. Did you draw a 7 or a diamond? So it's a probability of a 7. That is 1 over 13. Or because we're dealing with 2 different types, I'm going to go with the total number of cards. There are 4 7s out of 52 plus probability it's diamond. Well, there's 13 diamonds out of 52. And now we need to subtract the one that is a 7 and diamond. Well, there's 1 card that is a 7 of diamond. So we're going to subtract that one to get 4 plus 13. Minus 1 gives us 16 over 52, which simplifies to 413. Next, what's the probability you draw a jack or 3? These do not overlap. You cannot have a 3 of jacks, right? So 4 over 52 plus 4 over 52 gives you 8, which is 213. Moving on. Independent events are if the occurrence of one event has no impact on the occurrence of another event. Like if I rolled a 1 on a dice and flipped a coin and got heads. Those don't affect each other. If A and B are independent events, then the probability that A and B will occur is given by if P of A then and B is probability of A times probability of B, right? So you're multiplying here. A couple examples here. 70% of students who take Calc 1 in college receive a B or higher. 90% of students who take Physics 101 in college receive a B or higher. What is the probability that you receive a B or higher in both classes? Assuming all students must take both, right? So we're going to do probability, which is 70%, we're going to write 0.7, 90% 0.9. So 0.7 times 0.9 is 0.63. Next, probability of a complement is 1 minus the probability that the event happens, right? So probability that, we get a heads would be 1 minus the probability of getting tails, just as an example. So Next, in high school, 60% of students will take at least one AP test. What is the probability that a high school student doesn't take a test? Well, that's going to be 1 minus the probability that they take one or more tests, right? So 1 minus the probability of at least one, because that counts for people who take one or two or more, gives you 1 minus 0.6, gives you 0.4 is our probability. Next, a watch manufacturer has determined that a certain machine averages one faulty watch for every 100 watches produced. What is the probability that an order of 250 watches will have one or more faulty units? Okay, well, one or more. So technically, what we would have to calculate to do this one is enormous. We'd have to do probability of 1 plus probability of 2 plus probability of 3 until we get to 250. And then add all those numbers together. Well, that would take a long time. So how can we use complement to make it quicker? So what we want to do here is do 1 minus the probability that we have no faulty units, right? Because this would be, what if we got through with scotch-free and didn't have any faulty units? So 1 minus the probability of none will give us the probability that we have a 1 or more. And so we get 1 minus the probability of none means that we have that 99% chance of getting a good watch, right? One out of 100 is 1% to get a bad watch, right? So 1 minus 0.99 every single time. So 250 is where that comes from. Each unit gives us a 0.91894. And so it's a 91.894% chance that you'll have one or more faulty units in that 250. Next, find the probability in an experiment of drawing 3 marbles without replacement from a bag containing 3 red, 4 blue, 2 green, 1 yellow. What is the probability all the marbles are blue? Now, in these types of problem, you want to total it up. So 3 plus 4, 7 plus 2, 9 plus 1 is 10. We have 10 total. And so the reason why that's important is because our bottom number, our total number of ways to do this would be, we have 10 combination 3, right? How many groups of 3 can we make? So it's a combination. Now, how many ways can we get blue? Well, we're going to have 4 blue options, and we're going to choose 3 of them. So 4 combination 3 over 4 combination 10 gives us 1 over 30. Next up, find the probability in the experiment of drawing 3 marbles. Same idea, but now we're doing the probability that all marbles are different colors. Well, so what are the options for different colors, right? We could do red, blue, green, red, blue, yellow, red, green, yellow, blue, green, yellow, right? Those are the 4-ish combination, I think. 1, 2, 3, 4. I think I counted 4. So then what's the probability of red, blue, green? Well, 3 choose 1, 4 choose 1, 2 choose 1. Plus the probability of red, blue, yellow. Well, 3 choose 1, 4 choose 1, 1 choose 1. Plus probability of green. Doing it the next one, red, green, yellow. 3 choose 1, 2 choose 1, 1 choose 1. And now in general, these are going to be 3, 4, 2, 3, 4, 1, 3, 2, 1, right? That's basically what's going on here, but this is the math behind it. And then the bottom is 10 choose 3. And so totaling these up, we've got 24, 12, 6, 8 for these, right? 3 times 4 times 2, 3 times 4, 3 times 2, and so on. 50 over 1/20th gives us a total of 5/12 probability. What about none of the marbles are green? Well, this is a complement one. This is 1 minus the probability of green, or we could just do how many marbles aren't green? 3 plus 4 plus 1 is 8, or total minus green. And so we have 8 non-green, so we're going to have 8 choose 3 over 10 choose 3. Which gives us 56 over 120, or 7/15. Now the last one's a tricky one. We want to have 2 of one color and 1 of another color. Now, what colors can we have 2 of? This is the easiest way to do it. There's more than one way, but having done it both ways, this is by far the shorter way. Well, we could have 2 of red, and then 1 of whatever's left. We could have 2 of blue and 1 of whatever's left, or 2 of green. We can't have 2 of yellow because there's only 1 of them. So the probability for the red would be 3 choose 2 of the red, and then there's 6, 7 left over, or 10 minus 3, that we're choosing 1 of. And that would cover all the ways we could have 2 reds, 1 of another. Same thing with blue, 4 choose 2 times 6 choose 1. Why did that number change? Well, we had 4 blues. We don't want to put the 2 extra blues back in the mix. So we're doing 4 choose 2, 10 minus 4 is 6, choose 1. And last one, same thing with green. We get all the green ones and then 8 other options for a total of 13/24 is the answer.